All right. We're here tonight with Dr. David Zaslavsky. I practiced and I still messed it up.
We're doing so well.
Dr. David Zaslavsky, and he's going to give us a seminar this evening on high energy physics, talking about interactions of protons and protons, what's inside the proton. David has a very interesting pedigree. He's coming from Princeton with a degree in physics and a concentration in applications of computing, which definitely reflects what we push to get you guys to do some computational physics. He got his degree in his BS in physics in 2008, and he has just gotten his PhD from Penn State University in their nuclear and particle physics area in 2014. His dissertation title was Probing Hadron Structure in Proton Nucleus Collisions. So David is right now a postdoctoral research fellow at Central China Normal University. So he is he's actually in California right now, David. Is that correct?
Yeah. Yep, that's correct. I'm Berkeley lab.
He's going to head back to China for continuing work on his postdoc
audio
in a few minutes. Do you have an audio back?
Yeah, now it works.
Okay.
Just a moment there, it was coming through badly.
Okay. Hopefully we can avoid any more problems. So,
okay.
Thank you, David. We're looking forward to your seminar. Please take it away.
Cool. Okay, great. Well, it's nice to see all of you, except Will, apparently, on the screen. Okay, I know you're there. But yeah, this is it's a honor to have this opportunity, and it's a really great thing that you have going on here with these online seminars. I hope that more people take inspiration from this and try to do these kinds of seminars in the future, because it's easy, and it gives me a chance to share some fun information, and I should probably start sharing that information actually. So let me jump over to my slides. Screen share away. Okay. So, as I mentioned, I'm going to be talking about hadron structure. This is basically what we know about these, what makes up protons and atomic nuclei and similar particles like that. And so this is the project I've been working on since about my third year of grad school or so. This is what I did my PhD thesis on. I guess I would say you could read it, but who really wants to read someone else's PhD thesis? So anyway, this should hopefully be like a less boring and less technical description of what's going on, because there is some really cool physics if you can muddle your way through the math and really understand what's happening. Protons and nuclei are very, very interesting objects. So I'll just run down the what you see on the screen right now. This is kind of a summary of the research. I did it, I list me and my collaborators who I worked with when I was at Penn State. A couple of them are actually here at Berkeley right now, so I could probably pull them in to say hi if that was desired. But I just realized I made a typo, UCA, not UCS. Whoops. And I have so the papers, if you want to look up the original research that we did, I think it is those last two papers, primarily those last two papers from 2014. If you want to look them up, I think you can definitely, there are ways to get them freely available. I don't know if it's from the journal server or not, but if anyone's interested and has trouble finding them, just let me know. I'll be happy to point you to the right place. So by way of introduction, this is me, or rather, this is the picture I use everywhere online. Because it's kind of distinctive. In case you're curious, the jacket and hat are from the marching band uniform at Princeton. Actually, scramble band. We didn't really march. And so I do some things. As you've heard, my main job is as a physics researcher, a postdoctoral researcher. But I also do some science communication work like this, what I'm doing now, and I also kind of have a hobby of software development, which kind of ties into the fact that most of what I do for research is actually just writing computer programs. which I think it's certainly easier to understand than the actual physics sometimes. So I've listed here, I have a website where I write things sometimes about physics, ellipsix.net. I also post a lot on Twitter. I don't post a lot on Google+, but I keep meaning to someday. And some other things, I've been kind of involved in the science communication and education community online. So one of my roles there is a moderator on Physics Stack Exchange. I don't know if anyone's heard of Stack Overflow or the Stack Exchange network, but it's a network of Q&A sites on like 100 different topics. And so there's a physics site, and I spend some time on that moderating, and it's really boring work, but it's a great place to ask questions about physics. For kind of geared toward upper level undergraduates and above, all the way up to professors. And I've also been somewhat active on physics forums and on Reddit. I know despite the image of Reddit, that's actually kind of a good place to get questions answered sometimes. So these are things that are kind of not part of the traditional academic track, but people these days do a lot of these things, and it is it's a good way to understand some science. So basically to put my history in context of the typical academic career track. So I don't know if maybe everyone knows this already, but for people who want to go into academia or think they want to go into academia, you start with an undergraduate degree that's typically 4 years, and then you move on to grad school, which is, they tell you it might be 4 years, but it's actually around 6 years, sometimes more. I've heard going more than 10, but that's kind of crazy. And then, so people who come out of grad school, the ones who want to go into academia typically go on to do postdoctoral positions, which, like the thing I'm doing, it's a temporary 2-year position, which is just a chance to move around, to work at a different institution, gain some experience with new people, and to try to build up your reputation in the community. And so it's usual to do 2 postdocs or so, lasting for maybe 2 years each, sometimes 3. And then after that, people who want to go into academia will transition to a tenure track position. And so, it's just applying for a job. You get a job somewhere. Now, what I've done, I've put the arrows here to show that actually at each stage of this pipeline, lots of people don't go on to academia because it's not exactly the most lucrative career, but it's also very, very competitive. And just the number of jobs available, these number of tenure track research positions are just very, very few. You might have like I think probably like 10 or, well, in the field of physics that I work in, there might be like 5 jobs a year, if that. Whereas the number of people coming out of grad school doing this work is in the hundreds every year. So as the width of the arrow shows, very, very small number of people who start out wanting to do this actually wind up doing it. Now, on the flip side, there are a lot of other things that you can do, coming off every stage of this pipeline. So, if you do an undergraduate degree in physics, but you don't want to go on to grad school, then there are plenty of other, industries that are happy to hire physics majors, at least so they tell me. Some industries do physics research. You can get into programming. As Will was saying, programming is a good skill to have. I know a lot of people who went to work on Wall Street, people who do data science, and people who become teachers, and there are many, many options. And the same thing kind of goes for people coming out of grad school. You can again go into a lot of these same opportunities, and people who finish postdocs, again, same thing. So there are many things you can do other than going into academic physics research. And I put this in here because a lot of people seem to not know that. I mean, it's not often publicized from the professors that you talk to at a university, because they're the ones who made it. Who made it into academic research. Now, and I guess this is how my timeline lines up for this. I guess Will went over this at the beginning, but undergrad at Princeton, I did grad school at Penn State, and then now I'm working at CCNU in this postdoc position, which is going to last about 2 more years. So just, a quick few words about where I work. This university in China, it's located in Wuhan, is the city, which is approximately where this red star is in relation to China as a whole. So it's kind of, it's about west of Shanghai, a few hundred miles inland. Wuhan is one of those large cities, 10 million people, that you've never heard of if you haven't been there, for most people. And the university that I work at, CCNU, is one of the top universities for particle physics in China, for this particular kind of particle physics. Now, China is still kind of a developing nation, but they are building up their economy and their science research very quickly, and they have a lot of money to throw at this problem. So that's one of the perks of living over there: low cost of living, and you get easy funding. And in case anyone's wondering, everyone speaks English in the physics department. So I don't actually know Chinese except for like a few words, which is kind of essential for working in China. I would not be able to do this if I didn't have people who I could communicate with, who can help me out when I need to go buy things or get food or whatever. But yeah, so there's that. Now, to fit what I do into the context of particle physics as a whole, so there are many, many different branches of particle physics, of course, and I kind of outlined a few of them here. Now, I could have gone on and made like thousands upon thousands of branches at every level of this chart, but they wouldn't fit on the slide, of course, and that's kind of a waste of time. But just to show, by the way, can you guys see my mouse pointer?
Yep.
Yes.
Guys? Okay. Yeah, so a lot of people have heard of the Higgs boson because it was big news a couple of years ago. People have heard of string theory because it's moderately big news every time someone decides to embellish their latest result. Some people have heard of neutrinos, but all these things are very widely separated. And I'm putting them here to make the point that they're very distant from what I actually work on, which is this part of QCD, or quantum chromodynamics. So this is studying the strong force, the thing that holds quarks and gluons together. And specifically, the part I'm going to talk about is the small x phenomenology, it's called. I'm going to explain what that means as the talk goes on, but basically phenomenology is kind of at the intersection of theory and experiment. So we kind of, it's almost like data-driven theory, I would call it. Instead of starting from first principles and trying to compute things from pure math, we're looking at the data that comes out of particle accelerators and trying to find theories that are consistent among all those different data sets. And so the specific thing I do, and we'll see how this fits into all this, I basically write computer programs to calculate integrals. And the broad overview is that so you take a theory, in order to compare that theory to an experiment, you need to get some numbers out of it, and that's where the integrals come in. So what I'm going to talk about is one particular example of how we do that. So I'm going to start by providing some background information, since this is a talk for people who are not already particle physicists. I'll say something about what we mean when we talk about the structure of protons. It's a thing called the Parton model that I'll go through and explain. And then, there it goes. So the Parton model is kind of a, well, it's something built on top of the foundation of quantum chromodynamics. So after explaining what we mean by the structure of protons, this Parton model, I'll get into how that is derived, or at least how it relates to the underlying, fundamental theory. And then I will talk about the specific calculation that we're trying to do. It's called inclusive hadron production. It can be called many things, actually, depending on who you talk to. But so basically, I'll show how we relate this theory to experimental results, and then I will present the experimental results themselves in connection with their data. Spoiler alert: this is the plot. But I'll explain what it means as we go along. And then, so as you may notice, this red curve here kind of goes down in a way that seems like it shouldn't, maybe, or if you can't tell, it shouldn't really do that. And so there is a question of how do we fix it, and now wrap up by talking a little bit about that. So this will hopefully give you an idea of the progression of a research project. Okay. So the underlying question is, again, what's in a proton? This is what the whole field of QCD and hadron structure is all about. Now, people often say protons are made of 3 quarks. There is a technical sense in which that means something, but it's not. I wouldn't say that. If you actually look at a proton or any small particle, it's made of quantum fields. And quantum fields obviously don't actually look like this. I mean, it's just a mathematical model. It doesn't really look like anything. But I put in the trippy colors just to for some artistic license. The thing about quantum fields is that they're not directly observable. So whereas if you had, so you may know that a field is something that has a value at every point in space and time. So a common example is like the temperature of the air. That's a field. You can go out and hold up a thermometer at any point in space at any time, and you will get a measurement of the value of the temperature field at that point. But there's no equivalent to doing this for a quantum field. You can't stick a magic probe into the middle of a proton and measure what the values of the fields are at that point. So the way we have to understand what a proton is made of how these fields work basically is by doing things to protons and seeing how they react. And that's the idea behind particle accelerators. Basically, you smash 2 protons together and see what comes out, and that tells you something about the configuration of the fields that make up the proton. And so when we do this, when you smash protons together, they wind up acting like a collection of particles, and that's kind of the nature of quantum theory. You may know if you've taken if you studied basic quantum mechanics, and you know about how wave functions collapse, and then you find a particle at a certain point with some probability given by the value of the wave function squared. When you collide 2 protons together, it works kind of like that. You have these quantum fields are sort of like wave functions, and when you hit them, there are turkeys outside the window for some reason. When you hit them together, it's as if each particle is kind of measuring the quantum fields of the other one in a sense, and so when they interact, they act like particles. It's kind of a good rule of thumb for quantum mechanics is a quantum field interacts like a particle but travels like a wave. And so when we hit these protons together and they interact with each other, they act like a big collection of particles, and those particles we call partons. Partons is a generic name for whatever happens to make up a proton. The name was invented in like the 1959, I think, when they didn't actually know what was in a proton, and so they called it partons because they're part of the proton. These days we know what those smaller particles are, and they can be quarks or gluons or photons or any sort of particle that we know to exist, and perhaps some that we don't know to exist if there are any such things. So partons is just a generic term for that, and then it's a word I'm going to be using a lot today, so remember what that means. So as I've been saying, the way we understand proton structure comes from colliding protons together in particle accelerators, and we keep building bigger and bigger, more and more powerful particle accelerators in order to get more and more detail about the structure of the proton. So it's kind of related to the uncertainty principle here. If you're familiar with this, you know that uncertainty in position and uncertainty in momentum are correlated, in the sense that usually the bigger one is, the smaller the other is. Now, that doesn't directly tell you that high energy particle accelerators are necessary, but you can kind of it at least the idea that these two things are inversely related, position and momentum, loosely suggests that if you want to understand the structure of something at a very fine scale, then you will need a lot of momentum or a lot of energy to do so. And that turns out to be true. It's not exactly a consequence of the uncertainty principle, but it kind of follows from wave mechanics. But in any case, the fact is, if we want to understand the fine structure of protons, we need to have very, very strong particle accelerators to do so. And so this graph shows basically the progression of how the energy of particle accelerators has increased over the years. Since the 1960s, it's basically gone up and up and up, and now we're at the Large Hadron Colliders, the current state of the art. And this is operating at, or it will eventually be operating at this certain amount of energy, which is 14 tera electron volts. And having access to this amount of energy gives us the ability to probe the structure of these particles in unprecedented detail. And I guess it may not be so important to go over this, but some historically significant particle accelerators. This Hera is one I'm going to come back to, because so earlier I said that as a phenomenologist, what we do is basically take input from existing data and try to run it through a theoretical model and compare it with new data. A lot of the existing data comes from this Hera collider, which operated up to 2007, and it's a very famous collider for that reason. And I'll come back to where that comes from. As far as what's happening these days, the colliders that we use for current experiments are mostly this relativistic heavy ion collider, which is on Long Island at Brookhaven National Lab. This was I believe, the first collider to do heavy ion collisions, which is a proton and an atomic nucleus. And as we'll see later, that turns out to be very, very useful for the kind of thing I'm looking at. And then, of course, there's the LHC, which is also capable of doing the same thing at higher energy. So what happens in a particle collision is the question. Well, you have two protons or two particles coming toward each other. And so, as I said, when these protons approach each other, when they interact, they act like collections of particles. And so if we arbitrarily designate one of these as the probe and one of these as the target, it doesn't matter which is which, if they're the same thing, then you can think of them as each of them as a collection of these little partons. And so it turns out that the collision event, like what you get that comes out, is mostly produced by one parton from the probe and one parton from the target. And so each of these partons carries some fraction of the proton's total momentum. And we use this variable x. It's yeah. So here I've written xp to mean the fraction of the momentum. So the fraction of the proton's momentum carried by the parton that comes out of it. This is these words using. And then xt is the fraction of the target's momentum, forward momentum, that the target parton comes out of it. So if you in some units, we measure momentum in giga-electron volts, which is, it's really a unit of energy, but the momentum is that divided by the speed of light. But people will often just say GeV. So this target might have a momentum of 7. Well, I guess at the LHC it would be 7,000 giga-electron volts divided by c, but people often don't say that. And then if the parton, like the quark or gluon that interacts from it, if that has like 1,000 giga-electron volts or 1 TeV of momentum, that would be 1/7 of the total momentum, and so it would have an x of 1/7. And so it's turned out to be useful to characterize the particles in this way, because even though you can't actually like stick a probe in, like a measuring device in the middle of the collision and measure this, you can calculate these x's based on what comes out. And the other thing you can calculate that's useful is this the transverse momentum transfer between partons. So basically you have the probe parton comes in this way, so this would be like a quark, and it hits a gluon, and then they bounce off each other and go sideways, roughly speaking. And because of quantum theory, they might do some other stuff on the way. But you basically get, two particles coming in, and then two particles or jets or something coming out. And depending on the collision, they could come out, perpendicular, or they could come out like nearly parallel. And the amount of sideways transverse momentum is a way to characterize that. And so this is the other thing that we can calculate based on what comes out of the collision. And so as I said, these variables. So if we're looking to understand, how the quantum fields in the target proton or whatever behave, then it's useful to basically calculate these two variables, xt and q, and this gives, basically calculating this over a large number of collisions gives us a way to understand the structure of this thing, this target proton. So going into detail about how that happens, basically, so when I said colliding particles act like collections of partons, I don't know if you may have heard, but in quantum field theory, one of the weird things about quantum field theory is that the number of particles is not actually a measurable quantity. So I mean, in everything else you do in physics, there are distinct particles, and you can always count the number of particles you have, but not in quantum field theory. This is quantum weirdness that a given system can actually have like a variable number of particles. It can go up or down, and that's part of what makes analyzing proton structure difficult. But it turns out that if you look only at collisions with certain values of x and q, then I'm glossing over a lot of technical detail here. But if you look at only those collisions, then the number of particles turns out to be something fairly well defined. And so, at a particular value of x and q, you can say, a proton is made of, this many quarks of this type, and this many gluons, and so on. So basically what we do is you collide particles together, proton on proton, and then you figure out the values of x and q corresponding to that collision, or corresponding to the partons that took place in that collision, that interacted. And then you just put it, basically see how often it happens, and you put it on this chart. So there are a few different possibilities. So at a low energy collision, what tends to happen is that so remember, one parton from each proton interacts, and they tend to have large fractions of the momentum. I guess you can think of it this way: if the overall energy involved in the collision is relatively low, then it takes a large fraction of it to make the particles do anything interesting. And so that's why in low, when the total energy is low, then we tend to measure collisions in which the interacting particles have high fractions of momentum. And at the same time, also the momentum transfer q is small, because that makes sense, because a particle that doesn't have much energy can't be moving that fast. And so in this limit, when the energy is low, x is large, q is small, the proton acts like just a few large partons. So the number of particles in it is basically small. For a certain value, it might actually be 3, and this is where the idea of the 3-quark model comes from. When people were first starting to investigate the proton structure in like the 50s or 60s maybe, they were worked a low energy regime, basically, that protons acted as if they were made of just 3 particles, 3 quarks in those days. And so we can put a little dot or a representation of a proton that is made of 3 quarks in the appropriate place in this diagram. So this is the band corresponding to low energy. That's large x, large momentum fractions, and small momentum transfer. Now, at a high energy collision, there are a few different things that can happen. One option is that the target momentum fraction x is large. So you can, if in such a collision, you might calculate that the fraction of momentum carried by the interacting parton is large, so it's a very high amount of energy, and that energy goes into producing a very large momentum transfer. So this is basically a collision in which a very high energy quark interacts with a very high energy gluon and sends something shooting out to the side with very high transverse momentum. And in this situation, the proton acts like, again, it might act like a collection of three quarks, but if you look at the data closely, I'm not going to get into this, but you find that they're actually very small quarks as opposed to large quarks in the other case. And so that's another one of the weird things about quantum field theory, is that the fundamental particles, they're not little balls. They actually, because they're fields, they act like they have different sizes depending on the conditions. So the other option, and this is still at high energy, is that if you're dealing with so if you run a collision and you find out that the momentum fraction of the interacting particle was small instead of large, then it turns out in those kinds of collisions, the proton winds up acting like it's made of a large or very large partons. And in this case, again, small momentum fraction means small energy, like not much energy to put into momentum transfer. So this is a collision in which a quark and a gluon, say, collide, and they don't shoot out to the side. They might just deflect off each other a little bit, and so you get something coming out very close to the direction of the original protons. And so this goes at the opposite corner of the chart. This is the small momentum fraction, small momentum transfer. And so if you go through many like billions or trillions of collisions and categorize them all like this, and you can build up a picture of how the proton acts in different kinds of collision. So basically, in a collision in which the interacting particles have small momentum fractions, it turns out that the proton acts like there are many quarks and gluons inside it. Conversely, in collisions where the interacting particles have large momentum fractions, so lots of energy, the proton acts as if it's made of only a few particles. And you can see that trend on the graph. The number of particles increases as you go up. And looking at it the other way, the size of the particles depends on this momentum transfer Q. So if the particles come out sideways with a very high amount of energy, that tends to be correlated with small interacting particles. Whereas if they don't go so far sideways, but if they go more or less straight, then that tends to correlate with large interacting particles. And so there are functions we call Parton distribution functions, which basically characterize the density of particles, or something roughly like it, as a function of these variables x and q. And so, an example of these plot these functions, over they're functions of two variables. And so if you plot them over the xq plane, then they shoot up as the number of particles gets larger. There's a different kind of Parton distribution function for each kind of particle. So there's one for up quarks, there's one for down quarks, there's one for anti-up and anti-down and strange and all others. There's one for gluons, which turns out to be by far the largest one at small momentum fractions. And this is the small momentum fraction is the area that I mostly work on. And so the gluon function is actually so large that you can just completely forget about the other ones. So for the rest of this talk, I'm going to basically be talking about the gluon distribution function, even though what I'm saying would technically or theoretically apply to the others if we were able to measure them. And of course, there are also Parton distribution functions for photons or neutrinos or whatever. Those are just so small, they're not really worth bothering with. And so this is basically the idea of the Parton model, is that we have these Parton distribution functions that can describe the effective structure of a proton depending on the parameters of the collision it's involved in. And this was all worked out in like the 1960s. Feynman was heavily involved in it. So now moving on to QCD. By the way, I would say feel free to interrupt me with questions, but I have a feeling because of the way the audio quality is working, that might not work out so well. So I mean, I don't mind if anyone interrupts, but there will be plenty of time for questions at the end.
Okay, sounds good.
I'm in a hurry. Yeah. So anyway, so we have this Parton model that was developed in the 1960s. And at this time, people still didn't know what the parts actually were. They just knew that there was something inside the proton, and sometimes it acted like it had a lot of them, and sometimes it acted like it has very few. And then, so in the 1970s, this theory, quantum chromodynamics, was invented. This is the theory that describes the strong interaction, the behavior of quarks and gluons. And so, this theory was basically invented along with the idea that quarks and gluons might be real objects. And so the question was, for these people who were working on the Parton model into the 1960s, when QCD became a thing in the 1970s, the thought on their minds was, can you derive the Parton distributions from quantum chromodynamics? Because it seems like you should be able to. If this is the theory that explains how quarks and gluons interact, and those are the things that make up protons, then it makes sense that you should be able to derive the behavior of protons from QCD. Well, it turns out that you can't really, but sort of a little bit. And so what I'm indicating by this chart is that you can't, like, Parton distributions at large values of x. So the behavior of the behavior of quarks and gluons that have large fractions of their parent proton's momentum, while in theory it should be able to be derived from QCD, in practice we can't actually do that because there are there are various difficulties. Some of it takes a lot of computational power. There are also some mathematical hiccups. It's kind of related to the idea of a divergent series. So like if you add 1 plus x squared plus x cubed plus so on, then if x is less than 1, that converges to 1 over 1 minus x. But if x is greater than 1, then it blows up, becomes infinite. And that's kind of related to what's going on here. This region on the left is kind of like a region where a particular perturbation series converges, and on the right, the red region is where it blows up, like the individual terms grow larger and larger. And so it works out that we cannot derive the Parton distributions completely from QCD. People are trying, sure, but they haven't really done it, and they don't really expect to be able to do it without some sort of mathematical trick. But you can derive the way they behave. So it's kind of like deriving the slope of this thing at small values of x. So QCD does tell us something interesting about the behavior of small x partons, so quarks and gluons with small fractions of their parent proton's momentum. And as I said, this is basically the kind of thing I work on, is studying these small x gluons. So the way QCD comes into this, I guess I should ask, how familiar are people with Feynman diagrams? I know it's a QFT thing, so.
Assume none.
Okay. Fair enough. So a Feynman diagram, you've probably seen them at some point, even if you don't know exactly what they are. And Feynman diagrams are basically a way of drawing the interactions among different particles that are involved in a collision. Now, the thing that makes this slightly weird if you're not used to it is that Feynman diagrams don't show an actual picture. And what I mean by that is, in a collision, you have one particle coming in from the left and one particle coming in from the right. I guess that's my left and my right. But anyway, they come in from opposite directions, and then they usually go out in opposite directions. But a Feynman diagram doesn't actually show the directions that the particle travels in. So in a Feynman diagram, typically it will show both incoming particles coming from the left, or sometimes from the bottom. And the way to look at a Feynman diagram is that it doesn't actually show you how the particles are moving. You only look at which lines connect to which other lines. So it only shows you the interactions between particles. So what I'm showing you here, about to show you, is this is a Feynman diagram kind of representing a process where, so you start with a quark. By the way, in case you didn't know, quarks have a property that we call color that has absolutely nothing to do with actual color. It was named that way because it's kind of like a version of electric charge where there are 3 charges. So instead of, well, actually 6 charges. The electric charge, there's positive and negative, but with this chromodynamic charge, there's red and anti-red, green and anti-green, blue and anti-blue. So this is showing a Feynman diagram of a process where a quark from the target, from the thing that's being hit, a red quark splits into a green quark and I guess just a red anti-green gluon. So gluons carry a color and an anti-color. You can kind of think of, like, photons kind of do the same thing in a way. They carry a charge and an anti-charge, but there's only one kind of charge. So a positive and a negative cancel out and give you nothing. And photons don't have any charge for that reason. But with gluons and quarks, because there are 3 different kinds of charge, not just one, it's like a 3-dimensional space, then you can have a positive of one color and a negative of a different color, and those don't cancel out. And so that's why I'm showing here. This is a gluon that has red and anti-green color charges. So basically this quark radiates a gluon, and then the gluon can split into 2 other gluons. This is going to be like, I guess, blue anti-green or something, I don't know, some combination of blue and green and some combination of red and blue. And then the gluon goes on to split and split and split until eventually it winds up interacting with something from the other proton. And as it splits, it loses momentum. So at each step, the momentum carried by this one, by the first gluon, has to be split between the 2 gluons it splits into, of course. And so every time it splits, it loses some momentum. And so that's how you. This is a thing that happens in protons, and other similarly behaving particles, called Parton branching, of course, by which the gluons lose their momentum, and so you wind up with a large number of these very small momentum gluons. And that's kind of intuitively why that Parton distribution gets very large as you go to small momentum fractions. And if I back up, so what I'm showing here in this circle at the bottom left is a different view of the same thing. So the Feynman diagram is, just shows the interactions. The circle is more of like what you would see if you were actually looking at this edge on, like as if the proton's coming towards you. So you start with a red quark, and then that quark splits into, so the quark is now green, and it gave off a gluon, which is represented by this line. Now, yeah, it's kind of weird to think of the gluon as a line. This is a thing called the color dipole model, which is, it models quarks as points and gluons as connections between points. And it's useful, sometimes useful as an analogy for thinking of how these splitting processes behave. So basically, the quark split into a quark and a line, and then when the gluon splits, that one line disappeared and 2 new lines took its place. And then so this line is going to disappear, the purple one, and 2 new lines will take its place. And then this blue line is going to disappear and 2 new lines will take its place, and so on. And I'm not going to get into it, but there is actually a technical reason for doing this. You can basically, if you were to do the math behind what I'm talking about, it would be useful to actually know how these points are distributed in the plane. And so that's why this color dipole model is useful, even though it maybe doesn't seem like it if you don't actually go through the calculations. Don't ever go through the calculations, they're a real pain. But anyway, well, I mean, here's a taste. The equation that comes out of it is this equation called the BFKL equation. BFKL stands for Belitsky, Fedin, Kurev, Lopatov, which are 4 Russian physicists who derived this thing in the 1970s. And of course, if you want to know more, just search Google for BFKL and lots of goodies will pop up. So it's a fairly complicated looking equation. It's got it's a differential equation, but it also has an integral on the right-hand side. But what it means is actually not nearly as complicated as it looks. So this S is basically related to the gluon distribution, or parton distribution that I was talking about before. And these formulas down here give the actual relationship, but it's just enough to know that it's related. And so what this equation describes is if you look at that colored model I was talking about, where you treat gluons as lines, gluon has a certain size, and at each splitting step, a gluon of this certain size disappears, and two gluons of these other sizes appear in its place. And these three sizes satisfy, they're the legs of a triangle, basically. And so this is what this equation is modeling, basically. You see the minus S term that corresponded to the original gluon. So this, the kind of tan yellowish minus S of X and RO1, that corresponds to the disappearance of the original gluon. And the blue and the purple terms correspond to the two new gluons appearing in its place. And this ratio of R's, RO1 squared over RO2 squared, RO12 squared, that basically gives the probability for this thing to happen given the sizes of the gluons involved. And so what it's saying is that this process can occur, and so you just add up, take a weighted, or like you add up the probabilities of all the possible ways this could happen in a proton. That's this integral. And then that tells you how the number or something like the number of gluons changes as you go towards different values of the momentum fraction. And so remember, when the gluon splits, then you're getting rid of a higher momentum and producing one with a lower momentum. So you're kind of exchanging large X gluons for small X gluons. And so it makes sense that if you model the splitting process in this way and turn it into this equation, it will tell you how the number of gluons changes as you go towards, as the splitting process proceeds towards smaller values of the momentum fraction. So that's basically what this means. It's hopefully that makes it make a little bit of sense, at least. Anyway, so this BFKL equation, it predicts that the number of gluons will grow as you go to smaller and smaller X, which is just what we saw happening. This is backed up by the experimental data that the number of gluons grows, or partons of any kind really. It grows as you go towards smaller and smaller momentum fractions. And so that makes sense as it goes, but eventually you run into a problem, and the problem is that at very small X, eventually, if this distribution grows too much, then it starts producing nonsensical results. Things like the probability of two particles interacting being greater than one. And I know quantum theory does a lot of weird things, but it does not account for it does not allow probabilities to be greater than one. And so, because this is what the model predicts, something has to go wrong with it. And I think what I plotted here is this is not exactly right, I think, but this is roughly an idea of this is an actual gluon distribution, and I think this is approximately the point at which we run out of experimental data. So the solid part of it, that's basically been measured and compared to experiments. The dashed part of it has not been measured, and if you extrapolate it, then it just goes up and up and up. And you can do some calculation to show that this growth is not sustainable. Something. So, obviously we don't want to conclude that particle physics is actually broken. So something has to happen to stop it from growing, so large. So I mean, this is a clear sign that this model ceases to be valid at some point, and it has to be replaced by a more general model. And so the more general model is one that takes into account something that the BFKL equation didn't, and that is recombination. So if you start with the same thing we had before, with a quark splitting into a quark and a gluon, and this is a large momentum fraction, then again the gluon can split into two. But now you're getting a bunch of gluons, and so if you on, then eventually some of these are going to start interacting back with other particles and combining. And so you have things like this happening. Again, this is in a Feynman diagram, don't look at the directions in which things are lined up. Just pay attention to the interactions. And so this shows that you have a gluon coming off here, but then a gluon comes back in and interacts with the quark, and like over here. And so now this is something that will actually reduce the number of particles as you go towards smaller and smaller x. So now the number of particles at small momentum fractions will not grow as fast because of this process by which particles combine with each other. And so this is going to lead to some sort of less strong growth at small x. So this function is not going to shoot up as fast as predicted in the BFKL model. This particular equation is called the BK equation for Belitsky-Chekhov. This was discovered in like 1995, I think. And now we don't know the exact details of just what happens here at the small x. Look, we know that this recombination process has to kick in and decrease the number of gluons, or at least keep it from blowing up so fast. But we don't know exactly how quickly it does that. This process, basically, what we expect to happen is that at some point, the rates of these two processes, the splitting and the coming together, will become equal. And then at that point, as you move to smaller and smaller values of the momentum fraction, then the gluon distribution will not grow anymore, and everything will be fine. I'm hearing some noise coming through from your end. Things okay?
Yep, we're good.
Okay. Just making sure. Yeah, because I can't see you, so I don't really know if something were to happen. Okay. So and the conditions under which the rates are equal. So the conditions under which the recombination balances out splitting, that's called saturation, because in a sense the number of gluons is kind of saturated. It reaches a maximum. This is the thing. This has technologies in all sorts of real-world systems. You've probably seen something that acts like this. And if you look at that chart, there's this region over on like the kind of top left corner in which saturation is supposed to occur. And this quantity, this line basically, that kind of marks roughly the boundary of where saturation occurs. This is called a saturation scale. It's a Q, momentum, as a function of x. And so it's very interesting to understand this function, the form of this function. This is something that we don't really know, because knowing what this is gives us a big clue about how particles behave in the proton. And so basically the broader effort I'm working on is involved in trying to figure out the form of this function. So in order to figure this out, there are certain kinds of collisions that make it much easier to understand this than others. And so this is basically to say why, I think I haven't mentioned this before, but we use actually proton-ion collisions as they're kind of the best probe. So you have, this is where a proton hits like a lead nucleus that has been stripped of its electrons. And the reason we do that is because the saturation scale gets larger when you're hitting a nucleus instead of a proton. And we want the saturation scale to be large because the interesting physics happens at smaller momenta. So saturation, the point at which these rates are balanced, it happens at small momentum transfers. And we want to be able to access those kinds of collisions, the top left of the graph. And so in order to do that, there are three things to do. We want to get as high energy in the collisions as possible. We want to get as large nuclei as possible. And we want to look at the small momentum fraction particles. So basically the particles that come out going nearly parallel to the way they went in. And if we try to optimize, look for collisions with all of those three properties, that gives us the best chance at understanding, what happens when this, the recombination balances out the splitting. So the particular calculation that I did, or what was involved in, I didn't do the whole thing, of course. It's this this thing called inclusive hadron production. And in order to explain this, I need to, I want to make sure everyone is at least vaguely familiar with how we describe collisions. So this is not like the earlier description where, I was talking about X and Q. That's how we describe the particles that are involved in the collision themselves. But it's also important to be able to describe the particles that come out of the collision. So these are the things that are actually measured by a detector. So here I have a picture of two particles coming in. Red line represents a particle coming in from the left, and a blue line represents something coming in from the right. So this might be a proton and a nucleus, for example. And then you have these three lines coming out from the center. These are outgoing particles. And so the detectors basically measure four things. Well, they measure more than the four, but we care about at least three of these four right now. So one of them is pseudo-rapidity, which is just kind of a different way of measuring the angle with respect to the original beam of protons. So infinite pseudo-rapidity corresponds to something that comes out going the same direction it came in. So if let's say if the two protons were to just completely miss each other and keep going straight, they would have infinite pseudo-rapidity. Whereas zero pseudo-rapidity corresponds to coming out perpendicular to the beam. And if you want, you can go to Wikipedia and look up the formula for pseudo-rapidity in terms of this angle. It turns out it's much easier to just work with the pseudo-rapidity instead of the angle. So for the things I'm going to present later, remember that large pseudo-rapidity means particles that roughly continue to go straight. The larger this eta, the more the particle continues to go in its direction. Whereas if eta pseudo-rapidity is close to zero, that means it completely changed direction and came out perpendicular. Another thing the detector measures is the energy of the particle. So it will measure it'll measure the amount of energy carried by each of these particles. This is done by a thing called a calorimeter. It's basically like a pot of liquid or something that the particle runs into and stops, and it heats it up. The particle heats up the liquid by a tiny amount, and there's a temperature sensor to read that. And the detector also measures a transverse momentum. Now, I think technically I kind of put these arrows in the wrong place because transverse momentum is usually measured in the middle, and it's kind of like a green cylinder. That's a silicon tracker. So basically, the particle flies through some layers of silicon, and it makes a little spark each time it goes through a layer. And so you get this pattern of spark, spark, spark that tells you what the path of the particle is, and from the properties of the sparks, you can extract how much momentum it had. So remember that a particle, for a given particle that has a certain mass, it has energy and it has momentum. And so there's one energy, there's three components of momentum. That's z is one, and then the x and y are combined into another. And so that's four variables, basically, that characterize the motion of a particle: energy and momentum. These things that I'm describing here, the fourth one being the azimuthal angle. So this is the angle around this way. These four variables, the pseudo-rapidity, energy, transverse momentum, and the angle, are kind of equivalent to that. It's an equivalent way of describing the exact same kinematic properties of the particle. We don't actually use the angle. I just threw it in here for completeness because it fills out the set of four. But this is usually ignored in particle physics experiments because the whole thing is symmetric. And so if you're just looking at one particle, in this calculation I'm going to describe, we only look at the highest energy particle that comes out of each collision. And so if you're only looking at one particle, it doesn't, the direction it comes out doesn't tell you anything. There are other circumstances in which it does, in which the angle is important, but I won't get into that unless anyone's curious. So the calculation itself. Now, the thing to know about quantum field theory, so we use quantum field theory to do this calculation. And basically the way any calculation works in quantum field theory is that you start by drawing these Feynman diagrams, which I was talking about earlier. And the diagrams you draw all the different diagrams for all the different ways that the particles involved can interact. And each diagram corresponds to a mathematical formula, and there's some combination of rules that gives you the formula corresponding to any given diagram. And then you take the results from all the different diagrams and you add them up, and that gives you something kind of like a wave function. And then you square it, and then you put it into another formula to calculate the scattering cross-section. Cross-section is something you might have encountered in like classical mechanics. It would be written as like d cubed sigma over d cubed omega or something like that. This is basically the same kind of thing, except instead of using angles in the denominator, we use this rapidity, or well, y is like eta, basically, pretty much. Pseudo-rapidity and the transverse momentum. So this is basically saying, we're calculating how often do particles come out with a certain amount of momentum in a certain direction. And so the formula that comes out of quantum field theory is made of several different pieces. This is actually, kind of an interesting result in its own right, the fact that you can break down the formula into different pieces that come from different parts of the collision. So there's a piece that corresponds to, picking one quark or gluon out of the probe proton. And so this is characterized by the Parton distribution. You can think of a Parton distribution, the same one I was talking about in the beginning, as kind of, it's like the probability of finding a parton, like a quark or gluon, with a certain momentum fraction in the proton in a collision where the momentum transfer is a certain amount. So this kind of acts like a probability density to pick out a quark with particular properties from this proton. Similarly, the same thing applies for the target. So we're picking out a gluon with certain properties from this target nucleus, and that's represented by this function S. We could also represent it by the original, like the F kind of Parton distribution, but doing so actually hides some information in a way that makes it less useful. But that's technical. So anyway, so there's a piece corresponding to picking out one particle from the probe and a piece corresponding to picking out one particle from the target. Then these two particles interact, and as I said, when you're calculating a Feynman diagram, you have to account for all the different possibilities of how these particles can interact, and then you wind up adding them up. I've drawn like two, I think, maybe three of them kind of superposed here. So this is just as an example to show that there are different things that can happen in this gray circle, and all the possible things that can happen in here, a formula for each one, and those go into one factor in the final formula. And then finally, the quarks and gluons come out of here, and then they turn into other particles on their way to the detector. I don't work in isolation, and neither can gluons. Because the strong force actually gets stronger with distance. And so if you try to pull a quark apart from another quark, then you have to put in so much energy that it just wind up making you quarks. And so the gist of it is that in the real world, quarks always come in groups along with gluons. And so by the time these things get to the detector, they're not just quarks and gluons anymore. They're like other particles, like pions or protons even. And anyway, there's a function to describe how the quarks and gluons that come out of this gray circle turn into the things that are actually detected. And then, so you write all those pieces, you add up or integrate all the possible ways this could happen. So like integrate over all possible values of the different variables, and then just add up all the different types of particles that could be involved. And that gives you a formula for the cross-section. This calculation is rather tedious. These days there are computer programs that can kind of help you help do it, but they are limited to the simple cases. But I don't know, sometimes kind of fun to play around with. But anyway, we do not have to get into that, thankfully. So the calculation that I was working on was this case in which a proton and an atomic nucleus come together. They have the collision of the partons, and then they produce a high-energy pion and other stuff that we don't care about. And so, one of the things we have to do in calculating this formula is, figuring out all the possibilities for what can go on in the gray circle. And so this is a thing that some people have been working on for several years. The calculations are, as I said, very tedious, and so it takes a matter of years to figure out a few terms. And so the simplest one, the simplest thing that can happen in the gray circle is, so you have a quark coming in from the left and a gluon coming in from the right, and then they just turn into one quark, and that goes off in some direction and turns into the pion that we detect. Or alternatively, you could have a gluon coming in from the left from the probe parton. A gluon coming in from the proton. See, it's easy to get confused. And a gluon coming in from the nucleus, and those could turn into a quark, and that quark comes out, and well, actually, I guess this can't really happen, but they could turn into another gluon. I just drew the wrong type of line, and that gluon could go on and turn into a pion or something that gets detected. So these were worked out some years ago. It's not that complicated as these things go, and then another year or so later, then some other people added on. They calculated the contributions from these more complicated diagrams. So this is where a quark comes in and a gluon comes in, and they not only radiate, they give off a quark, but they give off an extra gluon as well. And so there are all these different possibilities that can happen. And so some people added on these possibilities. So each of these gray circles corresponds to a part of the formula. And then now all of this has been done. People had run the calculations and crunched, gotten numbers out of these formulas, but none of the previous calculations included these ones that are shown in red. And so the project I was working on was basically the first one to get an actual numerical result that included all of these terms. And so what we want to do is, go through the numbers and see, how well does this formula that comes from including all of these different circles actually match the data. Of course, it's like a perturbation series. So these are the ones with one interaction. These are the ones with two interactions, or three in some cases. And as you know, the more terms you add to a perturbation series, usually the more accurate it gets. At least it should, in theory. And so the question is, these leading order terms are reasonably accurate. Question is, can you do more accurate by adding in all of these next leading order terms? And so now when it comes to actually showing the results, again, I guess kind of spoiler alert, it doesn't work, but it doesn't work for an interesting reason. So before we get to that, so there are two things involved here. Two things we're trying to show. One of them is we're trying to show whether adding all these next leading order terms, basically, does adding all of these next leading order terms actually make the formula better? Now that being said, so whether it does or not, then there's a separate input, which is this S, the gluon distribution from the nucleus, and the way we use this formula, once we're satisfied that it's accurate enough, is to basically make a guess at what this function S is. This guess might come from the the BK equation I talked about earlier, or it might come from something else, whatever you can come up with. So you make a guess for this function, plug it into the cross-section formula, and then see how well it actually matches what happens. So this is I mentioned this in the beginning, that we basically take a theory, plug in some numbers, and see how well it matches the actual results. So this is that process. And so there are two interesting sort of models for what you can do with this function. There's so the first one, this GBW model, as it's called. Golik, Biernet, and Wusthoff invented this in 1998, and they did this by just kind of, well, I'm not sure exactly how they did it, but by some reason they just came up with some function that when you plug it in, it happens to match data reasonably well. And they wrote this reasonably short paper on how to do this, and this was their guess at what S should be. It's just a simple exponential function. e to the minus r squared times the saturation scale squared over 4. And they also came up with this model for what the saturation scale should be like. This tells them how the saturation scale changes with x. And I remember, I was saying that's something that's interesting to know how protons behave, is how does this saturation scale, so how's the region at which the branching and the recombination balance, how does that vary with the momentum fraction? And so this was their guess. And they ran through some numbers, and they found that these particular values of these parameters in their equations fit the data the best. And the function acts basically like this. So this is showing a gluon distribution. It's like kind of the derivative of the gluon distribution I showed earlier. And so this shows the saturation here. So you can see this flat part at the left. That is flat because the recombination and the branching are balancing each other out. So it's flat because they're balanced, and then it kind of falls off because they stop being balanced and go to different kinematic conditions. And as you go to smaller and smaller values of x, so that's just like poor man's animation here. As you go to smaller and smaller values of x, you can see that the region in which the processes are balanced actually grows to higher and higher momentum. And so this is exactly what what we saw on what I showed on the earlier graph, or not a graph really. It was that chart with the different snapshots of the proton, and we saw how I drew the saturation scale as kind of increasing as you go up and to the right. Well, that's exactly what's happening here. As you go from large values of x to small values of x, this is moving up the chart. And as you move up the chart, the saturation scale, the point at which this falls over, moves over to the right. And so they made this particular guess at how exactly this thing increases, and comes up with this plot. And so it turns out that actually matches the data not too badly. They took some data from the HERA collider, which I mentioned earlier, that used to operate, and they fit to that data within a limited model, and they found good agreement with that. But that doesn't necessarily mean it's going to work for the thing that I'm working on, because I'm doing a different calculation. Maybe what works for them is not going to work for us. So we'll see that later. The other alternative, so the other guess for this gluon distribution S I'm going to talk about is the one that comes from quantum field theory. So this has to do with those branching and recombination diagrams I showed earlier. And so if you run through all the calculations from that, then you wind up with this function, which looks very different. Now this part where it kind of disappears over around 10 to the third, that's a numerical artifact. This one, there's no nice formula for it. You have to plug it into a computer and get the numbers out. And the computer, when you're dealing with too small numbers, then the computer kind of flakes out. And so that's why this is happening. It's not the case that the function actually disappears for a while. But you can still kind of tell what it's doing before it gets to that point where it goes crazy. Unlike the previous model, which dropped off very steeply, this one kind of drops off not so fast. It's got a much gentler slope. And it also doesn't move over to the right as fast. So this is an example of how basically the saturation scale, so we're trying to figure out how the saturation scale changes with x. And so that is like how fast does this hump move over to the right. And in this model, it moves less fast than in the GBW model. And so this is an example of we're comparing different models and trying to figure out which one matches the data better, and that will tell us something about which of these models more accurately describes the content of a proton or a nucleus. And so this is the results that actually come out. These are, I should say. Now, so the thing about my field of particle physics is that this is about, these are like the prettiest pictures we get to make. We don't have like the people who run the experiments, they get to show these awesome pictures of lines coming out through their detectors. Or people who do astronomy get to show their star and galaxy pictures. We just get colorful plots. So by the standards of this field, this is interesting. You'll have to take my word for it. But yeah, so anyway, this one is the GBW model. This is the one that drops off really quickly and where the saturation scale moves quickly to the right. And this one over here, the RCBK, is this Bielski-Kovchev, where it doesn't drop off so quickly, and the saturation scale doesn't move so quickly to the right, to higher momenta. And you can notice that the difference is really evident up at like high transverse momentum. So this basically shows how often a particle comes out with a certain transverse momentum. And you can see that as transverse momentum gets higher, particles come out less and less often. But just how they do that depends on the model. And so you can see this GBW model. Oh, I forgot to put the legend on these. So the ones with the cross shading are just from the leading orders. That's like the simplest formula. The ones with the solid shading are when you add in the next to leading order terms. So that's depending on whether you only include this. So this is the cross shading, but all of this is a solid shading.
That kind of makes you sick, doesn't it, David?
Yeah, yeah. Well,
unfortunately.
Okay. Yeah. My computer was worried. I was worried it might go a little haywire there, but it's okay. But yeah. So anyway, the point is that these black points these show the actual experimental data that come from an experiment at the relativistic heavy ion collider. That's the one in Long Island. And so you can see, if you look closely, you can see that this GBW model kind of overshoots it at small momenta and undershoots it at high momentum. Where the BK, the RCBK, the one that's based on the quantum field theory, it's a little closer. So it's more accurate at small momentum, and it's still low, but it's less low at high momentum. And so you can really see the effect of remember when I showed that gluon distribution, like this one here, it doesn't drop as slowly. You can really see how that shows up in the experimental or in the results of the calculation. And so see, this is a way. This is telling us, something about the structure of the protons based on this data. The experimental data, they don't drop, and so we know that that tells us, if this formula is accurate, that the gluon distribution probably doesn't drop, maybe even slower than this. And so this is again, the process we've gone through is that you make a guess at the function s, and then you plug it into a model, and you see how see what comes out and see how well it compares to the experimental results. And this is what happens. This is how you understand what the structure of a proton is. It's very abstract, but this is what we are forced to work with by the quantum theory. So this is another set of results. The one on the right is the scale is a little different, but it's the same thing from the last slide. The one on the left is at a different pseudo rapidity. So remember this eta represents how close to the beam line the particles come out. And so this graph on the right shows particles coming out very close to the beam line. So these are things that are barely deflected at all. They just they kind of nudged off each other but kept moving. The one on the left shows particles that were nudged a little more. And so you notice the next to leading order term. So when you add in all these extra Feynman diagrams, it really makes things kind of terrible. And when we first got these results and found that the cross section it calculates is actually negative, because that's what happens. It actually drops down to 0 and then becomes negative, and you can't see it because it's a log plot. That was very confusing at first, because a cross section is not supposed to be negative. That's like it's like a probability being negative. So that clearly something fishy is going on here. So as the slides are showing now, what's the deal? You wouldn't think a formula for something that's obviously positive should be able to produce a negative result. But it's actually not as weird as it looks at first glance, because remember, this is a perturbation series. So we had those leading order Feynman diagrams, and then you had the whole next leading order Feynman diagrams with more interactions, and then there are more and more orders beyond that. Now the number of these diagrams gets far, far larger as you increase, and so they become much, much harder to compute as you go, as you bring in more of them. But they are out there, and so this suggests is that you have to pull in just the leading order and next leading order diagram. Like the first two terms in this perturbation series do not give a sensible result. It's like, as I was saying earlier, if you add 1 plus x squared, etc., and the result is 1 over 1 minus x. But if you just add 1 plus x, that's clearly not the same thing. So it does kind of make sense that if you're omitting a lot of terms from the perturbation series, you may not get a sensible result. We were kind of hoping that all the rest of the terms would be small, and so we didn't have to care about them, but evidently that is not the case. And so then the next, the logical follow-up is then, what can we do to get a more accurate prediction? I mean, something is, we obviously can't make sensible predictions by just, omitting the rest of this terms from this formula. So what we have to try to do is, if these aren't enough, then we have to pull in, some contributions from higher orders. So some of these more complicated Feynman diagrams must be having a very large effect on the predictions. And now, if we can figure out just which ones are the most important and only calculate those, then it saves a lot of effort. Whereas calculating all of them is impossible, but maybe just calculating 1 at each order or 2 at each order, that might be reasonable. And so I won't get into the details of how we did that, because I know this is really kind of a long talk already. But we actually did try this. I'm pretty sure this is mislabeled, and the black thing is the data again. So we actually did try putting in some formulas from higher order terms. So incorporating some things like these these diagrams, multiple loops. So this is just like, what if this happens? We can alter a formula to incorporate that. And there's like a parameter. When we do this, there's a free parameter that we have to set to figure out like how much of an effect do these higher order diagrams actually have, because we're kind of like cheating and trying to calculate them without really calculate them in a way. And so there's some uncertainty in how we should actually do it. And so the value of this parameter c kind of reflects that uncertainty. We can tweak this to different values to see what gives the best results, and then maybe that maybe it's like we're doing a hack and we have to tune it. So you can see that okay, so this is the plot that makes sense. For this, in this plot on the right, where you have particles coming out very close to the beamline, if we do this correction, then it helps at the high momentum. So the particles that come out with a lot of transverse momentum, now we can calculate that result. It seems to work fine. But the ones at low momentum, now it's way, way above the data. And so this makes it worse at low momentum and better at high momentum. Conversely, for this plot on the left, this is for the particles that come out not so close to the beamline. The whole thing is just a mess. And so, this is something we tried. Obviously, I skipped over the the details of how it was actually done, but we ran the numbers, and this thing turned out to be really messy, and it was just kind of a false start. So this is something that happens in science. So what? But well, now we've established something that doesn't work. So time to try something. Oh, I think it froze. Okay. Yeah. So it kind of helps in some cases, but we could do better. So the other thing we tried. Now there are a tremendous number of approximations that go into these calculations, and that's something that makes it very one of the things that makes it difficult is keeping track of all these approximations and knowing, when did you do one that actually doesn't work or is getting in the way of your result or something. And so one of these approximations so this is a Feynman diagram. It shows a quark coming in. So this quark came from the proton, but I didn't show it coming from the proton. Quark comes in, it interacts with a gluon that came from the nucleus. And so this red dot is where the quark and the gluon interact. They come together for a moment, and then this quark gives off a gluon at the blue dot. And so we used to assume that the transverse momentum of this gluon was negligible, but that actually doesn't work out. That kind of spoils the calculation. And unless it's it works if the energy of the colliding particles is infinite, because then this transverse momentum is small compared to infinity, but it's not actually infinite in real life. I mean, at RHIC, the collider on Long Island, the energy is of the colliding particles is 200 gigaelectron volts, which is very far from infinity. Although I did have a professor who used to say that for purposes of physics, infinity is 5 or maybe 10, which works a lot more than you'd think it does, but not in this case. So infinity is a lot greater than 200, and so it turns out making this approximation actually kind of spoils things. And so again, I won't go through the details of how we derive this, but we can make a new calculation that does not use that approximation, and it turns out to actually work pretty well. So this sort of fixes the difference between, it still sort of overshoots it a little at the high transverse momentum, but you see this is a lot better. In particular, the fact that it's not negative is a very good sign. Yeah, so that's maybe a rule of thumb. When your results are physically possible, you're doing well. And so one of the approximations we actually made in deriving this new result was something that makes it work only at high momentum. And so it stands to reason that this green result should kind of work at in fact, that may be my next slide. Yeah. So at low momentum, the new result that we got with this with not neglecting the gluon momentum, that is that overshoots at small momentum, but that kind of makes sense because we made this approximation. That means it shouldn't work here. So the original result, this red thing, kind of matches the data at low momentum. And then when you go to high momentum, then the green one matches the data. And so that, between the two different calculations, we've kind of patched together a way to describe most of these experimental data, which is basically what we wanted to do. So, I mean, it feels very hackish, but we managed to piece something together in the end. And this is kind of an interesting result because it is the most accurate formula to describe this particular collision that has been developed so far. Actually, we're working on yet another addition to the formula, but that's I've gone on long enough about this already. So after all that abstract talk, I mean, the question is, what does this tell us? So there are three things that could possibly have concluded. First of all, one possible conclusion is that the cross-section formula is simply not precise enough. So this formula we're basically using to relate. So when we make our guess at S, the function S, which describes the structure of the nucleus, we take that guess and plug it into this formula, and we get out something we can compare to experimental results. If the formula is not accurate, so like if we need these higher than next leading order terms, then we can't do anything about that. It gives us no way to actually compare a guess for S to the experimental data. If we can make the formula precise enough, which is what we think, this exact kinematics thing, as we call it, then comparing the result to the experimental data shows us whether our model of the gluon distribution is accurate or not. And so if you remember back to that plot I showed with the GBW model, in fact, I can jump back to it. Yep, that one. So this is a case if we use an accurate formula to calculate these predictions, then here you see this model, the GBW model, is not accurate, whereas the RCBK model is kind of accurate. And so by comparing, then that tells us something about how the proton behaves on the inside. And so I guess, I don't know, since I don't know if I put it quite this way anymore, but this next leading order formula is, it is useful for something, but it needs like some extra tuning to be better. I don't know. Overall, this is kind of nice because we did manage to find something, we managed to find a formula that seems to work over a wide range of this transverse momentum, and we managed to find a model that we can plug into the formula that seems to work over a wide range of transverse momentum. And honestly, this is about the best you can hope for because particle physics is a huge mess, and extracting any sort of sensible result out of it is honestly, it's kind of a blessing whenever you get anything to work. So that's all I got for that. Unless anyone wants to see the formulas, which are in my extra slides, but that is it. Thank you for your attention. Anyone who's still awake.
All right, let's thank our speakers. Okay, so just as a quick announcement, if you're watching online, I turned on the Q&A feature, and so Dave, if you would click your mouse over to the left-hand side of the screen and push the Q&A button,
okay.
See a looks sort of like a chat window pop up. If you're watching the Google Hangout from Google Plus and you have a question, you can type it in there, and we should see it and be able to answer it. If you also have a question on Twitter, you're watching the YouTube stream and you have a question on Twitter, just use the hashtag GHO Seminar, and David or I will find it, and we will ask it. David, you have your Twitter up?
Yep, I'm pulling that up now.
Okay, so we'll watch and see if any questions pop up there. And so we'll open up questions to the room first, and then see if anyone has a question online. So do we have any questions from our student audience here?
Sure.
I have a question about just the practicality of detecting partons. You mentioned calorimetry, you mentioned the silicon. What other
well, I mean, that's kind of a little out of my area. Yeah, that is experimental technology, and I'm really more of a theorist. So I don't know the full details of how that works. But let's see. So these detectors are basically built in layers. So like and each layer measures different things about the particles that go through it. So the actual collision takes place right in the center of the detector, and then the particles come out. Now keep in mind, we're not actually detecting partons. So the partons are the quarks and gluons. Those are the things that are inside the proton. And remember that they can't exist on their own. So if you try to pull them apart, say by smashing them into each other, then they will just make more of themselves and combine into bigger particles. So by the time any of these particles manage to touch the detector itself, they have already turned into something, something composite, like another proton or a pion or something. So now the detectors are built, like different detectors are built in different ways, and they're usually built for some purpose, and the purpose affects how they're built and what layers go in and in which order. So, for example, like the detectors at the LHC, there are a couple of general purpose detectors there, Atlas and CMS. I don't know if you've heard of them. But anyway, that's what they're called. You can look up lots of information about them online at all different levels of technicality. But those are general purpose detectors, and so they're built with kind of a standard set of components that allows them to characterize whatever comes out of the collision. So like the innermost layer is this the silicon tracker, where you have, like I said, it has multiple layers of silicon, and the particles make a spark every time they go through a layer, and so you can, track its path as you go through it. This is, I guess, it's like the modern equivalent of a cloud chamber, kind of. And so the particle will go through the silicon. Only charged particles actually leave a track fit. So it will go through that, and then it runs into, so they have electromagnetic calorimeters and hadronic calorimeters, and each of those will stop different kind of particles. And so all these things are instrumented with sensors so they can tell when a particle runs into them. And so there's like, I don't know, 4 or 5 different layers, I think, in each of these detectors. And each one detects some different properties of a particle, and then they have the computer algorithms that kind of reconstruct what the actual particle was. So that's, I mean, I know that's kind of on the side of what you were really asking, I think. I don't know. Does that help, or?
No, that helps. I realize you're more on the theoretical, but I'm just wondering. I mean, I have no idea about how you possibly detect something of this nature, but that kind of reveals a little more. So, thank you.
Okay. Oh yeah. It's it's all like very tiny atomic or subatomic level interactions. Like I said, there's a lot of stuff online that you can read. In particular, both of the big detectors, the Atlas and CMS at the LHC, these are like, the detector itself is a big machine, but there's a big collaboration of people who support that machine. So like Atlas has 3,000 people working on it. Not all of them work on the detector itself. Most of them do like data analysis or design or construction, and they're spread out all over the world. But it's such a big collaboration that they actually have their own PR department, and so they put out educational materials, that are even that at every level, from physicists down to complete lay people, and they describe, some of these describe how the detectors work. So if I remember correctly, the website is like atlas.cern.ch or something, but I mean, if you Google it, they will find it right away. And there's probably more information there than I can give you on how exactly these things work.
Okay. David, can you see that question there from Matthew Fikert?
Yeah, let me take a look. Oh, this from Twitter?
No, I just selected there. It's, David, can you comment on your experience, how you view the role of machine learning in high-energy physics over the next 5 years? You see it?
Okay. Wait, there's a Q&A button. Wait, what did I do? Okay, I see it now.
Okay.
How I view the role of machine learning in high-energy physics. So this actually does find some use in phenomenology. Basically, particle physics is just getting more and more complicated, and there's just always more and more data to process. And so we rely more and more on computers and more on increasingly sophisticated computer algorithms. And of course, machine learning is kind of the natural cutting edge. So like, of course, people are going to use it more and more. One example I can think of is, so the Parton distribution functions that I measured, that I mentioned, there are different groups of physicists around the world who basically make it their job to measure the Parton distribution. They don't actually measure them even. Like, that's another instance of they come up with a guess at what kind of function it is, and then they try to fit it to the data. And different groups have different ways of doing this, and so it's not just like there are Parton distributions. There are different sets put out by different groups, and they're a little different. And one of the big ones actually is the NNPDF, neural network Parton distribution function collaboration, and they use a neural network to kind of try to optimize the best fit for the Parton distribution without I guess they have to make some sort of a guess, but they try not to let their result be influenced by what kind of guess they make. And so that's one application of kind of something that approaches machine learning in phenomenology. And I think it's it's kind of a new thing, because physicists are mostly physicists because they're not programmers. But I think as time goes on, we're going to see more and more of this machine learning and advanced computer algorithms becoming more essential in all areas of particle physics. So that's my thought.
Do we have any more questions?
Yeah.
I've got one. You mentioned the pseudo-rapidity, and in acoustics and geosciences, we sort of have a similar name, rapidity. It's used to denote like 1 over the wave speed, 1 over the speed for a particle or speed for a wave. Is that sort of the context? Is it like 1 over the transverse momentum or something like that? Is that related?
I don't think it is offhand. It might be related in some way that I'm not realizing right now. But the pseudo-rapidity, it's like the logarithm of the arctangent of half of the angle, something like that. Yeah, so I don't think it's. I think it's just a similar term for a totally different thing.
Okay.
But I can't be sure.
Okay.
I don't know. That's interesting.
Yeah. Yeah. It's when you're doing seismic, you can measure times, from when the wave arrives, and so you're more easily able to measure that rather than the distance traveled. And so it's more convenient to talk about 1 over the wave speed versus the speed of the wave. So that's the context in at least seismic acoustics where that word comes in.
Yeah.
So you've got an audience of undergrads, so they're looking at grad schools or other potential technical careers to go into. What advice, if you could go back and talk to yourself at this stage, what advice would you give these young people?
Okay, well, that's a good question, because I know I probably lost everyone with that talk. I mean, particle physics is just inherently complicated. I'm almost tempted to say don't go into particle physics, but I wouldn't say that, because it is actually really interesting if you can figure it out. Let's see. So the #1 piece of advice I would probably give, because I didn't know this, is that when you're applying to grad school, if you want to do well at it, think of it more as applying to work with a specific professor rather than just applying to school. So going into a PhD program, it kind of winds up being like a research job eventually. Like the first couple of years you're taking classes, and it's pretty similar to undergrad. But the whole point is the intention of the program is to prepare you to be able to do research. And so the faculty kind of look at it as a job, where you kind of you spend some time getting trained, and then you are becoming a worker. And so what they like to see on grad school admissions committees is that you have that there's something particular you want to work on. It's not just, oh hey, I want to go to grad school because I like having a PhD. They are looking for like each professor is looking for students who are really interested in doing that kind of work that the professor is doing. And the best thing you can do for grad school admissions, or I've heard, is to have someone inside the department who actually wants you to come there. So if you make, for anyone applying to grad school, if you make contact with a professor in advance, like someone who is doing work that you would actually want to work on, and if you can, build a rapport with them, let them know that you would like to work for them, and hopefully get them to think they would like you to work for them. Then they will kind of go to bat on your behalf when the admissions come up, and that's like one of the best things you can do is have someone saying, I want this student to come here and work for me. So Yeah, when I applied to grad school, I kind of treated it as just applying to school. So I just, I looked up what some of the good schools were, and I sent out applications, but I didn't really have a specific thing I wanted to work on. You can certainly make that work, and a lot of people do, but you have better chances if you have, some idea of what you want to do. The other thing I would say is, make sure you know what you're getting into before you get into grad school, because PhDs are meant for people who are really dedicated to a specific topic and want to study it in detail. And like I said at the beginning of my talk, the academic job market is not great, especially in theoretical physics. There's so few opportunities available, and so I guess I would say to anyone going down that route, be aware that it certainly has a lot of big perks if you can get it, but also be aware that the odds are not in your favor really, pretty much no matter who you are, and so getting a physics PhD is actually pretty good preparation for all sorts of other things. So it's not like your life is over if you get a PhD and then don't get an academic job. But be aware that you might not wind up doing what you want to do, and that's okay. And anyone who is not planning to go into academia, I would say don't let anyone make you feel bad for not wanting to go into academia. Professors sometimes have a tendency to to look at the people who want to be future professors as like the only ones who are worthwhile. I think it's less so these days than it used to be. But I don't know, like there are all sorts of other things you can do other than just becoming like a research professor at a top university that are totally worthwhile and good choices, and so something to think about.
Okay. Do you have any other questions from our audience?
Yeah.
So you do a lot of programming. What language do you program in?
Well, that depends on the task.
Okay.
Question, actually. So the code that I wrote to calculate the results for this project that I talk about, I did that in C++, because it needed to be fast, and C or C++ is generally fast. But also from time to time, I often use Mathematica, which is when you want to just do a quick calculation without like writing a whole C++ program. Then Mathematica helps you with that because it's a programming language built to do math. For data analysis, I use a lot of Python. Python with NumPy and IPython notebooks is actually very, very useful. I've gotten to, in this project, in cases where it was useful, I've used like all sorts of arcane Unix scripting languages. That's maybe just like my thing. Most physicists don't do that.
So I mean, was that all running on just your basic laptop or desktop, or those jobs submitted to a supercomputer?
So the calculations I did for the project were actually run on a cluster, a computing cluster at Penn State.
Okay.
Because each run of the program takes maybe 3 or 4 hours, and then we have to run it like 50 or 100 times because we do like a integration. I don't know what Monte calls, but it's basically you take random numbers and sample a function at random points and use those samples to calculate the integral of the function over like 10 variables or whatever. It's a technique that is very useful for when you're doing integrals with lots of variables. But the thing is, it's random, like I said, and so you have like random fluctuations, and you have to do a lot of different trials to make those balance, to kind of bring the fluctuations down to a manageable level. And so we have to run the program hundreds of times, and take the average in the end, in order to get sensible results. And so that needed a cluster. Some of the other things, like a lot of the data analysis scripts, I can just run on a laptop or a desktop. Yeah. Oh, I forgot one. I use LaTeX, of course, all the time. In fact, I actually made the presentation in LaTeX.
Yeah.
Which I guess a lot of people don't think of as a programming language, but it really is one. And actually, again, this is a thing that I'm kind of weird about, and most people don't do. But some of the data analysis was actually done in LaTeX. Like, the files come out from the simulation in a certain format, and I use Python to convert them to a different format, and then they get imported into LaTeX, and LaTeX does some final calculations to produce the plots. So it's it's really like a kind of harmony of different programming languages working together to make the finished product.
I've seen where you can run Python within LaTeX, and I know LaTeX can do some really basic looping and things like that. So how are you getting it to do more processing?
Well, I mean, LaTeX is actually it's a full-fledged programming language. It's painful to do so, but you can actually do anything a computer can do in LaTeX. It's Turing complete, as they say. So now the way I did this is with a library called PGF plots, which is for making plots, of course. It makes what I think are pretty good-looking plots. I mean, you can look at the plots that I showed and see if you like them or not. I think they came out reasonably well. And this library also contains the capacity to do some calculations. So it will read in columns of data from a file, and then you can add one column and multiply by another column or something. I guess I don't know that there's any point in me pop a file to show you, but the thing that comes out of the simulation has like a column for the leading order result, and it has a column for the next leading order result. And what I do in LaTeX is pull in the leading order number, multiply it by a factor, or no, I pull in the leading order number, pull in the next leading order number, multiply the latter one by a factor, and then add them together, and that makes the final plot. And this PGF plots library, it has like things set up to allow you to do those kind of calculations with some difficulty sometimes. It's finicky, but it produces very nice results when you get it to work.
Okay. Okay. So some of our students are in the process of learning LaTeX. Some of them are just beginning in learning Python. So that's sort of where, as an undergraduate, we fall back when you're a sophomore or a freshman and you don't know anything. And so you're learning and building these skills. It takes years to get proficient at any of that.
That's true. I actually have been doing things in LaTeX since, I guess, sophomore year of college. I started by, so I took a class on classical mechanics, like Lagrangians and Newtonians. And the professor said we could bring into the exam any notes that we create ourselves. So it was kind of like a semi-open book exam. And so I use that as an opportunity to learn LaTeX. I would just type up my notes, and when exam time came around, I would print them out and bring them into them. And so I guess that makes like what, 9 years or so, 10 years maybe. So I just use LaTeX for all sorts of things. A lot of some of the pictures I put in my blog post are made using LaTeX. I found, once you get into the arcane details, it's actually useful for a lot of different things, and it does make really good-looking documents.
Oh yeah.
But yeah, it takes a long time.
Okay.
But yeah, I mean, like you said earlier, any of this programming experience, this is something that can make you marketable, outside of physics. So this is, like people, if you want an academic job and but if you don't wind up getting one, you can also fall back on programming experience. And if you don't want an academic job, then whatever you wind up doing, pretty good chance programming will be useful. So it's like the new literacy. Or so I've heard it said. I don't know if that's quite true, but
well, it's
certainly something
similar to sort of the way I refer to it with students. You learn your theoretical physics. You've got your analytical way of solving things, right? You have your experimental side of figuring things out. Well, computation is like your third arm. It can come out and it can help you solve problems that you can't solve with the other two. You know,
yeah, for sure.
You're not solving these integrals by hand on a piece of paper. This is all done in a computer.
Yeah, nobody wants to do that anymore.
No, well, you can't. There's no way.
Yeah.
It's impossible.
Yeah.
But yeah. So, any other questions from our audience or online?
Yeah. Anything about, like, even if it's not about physics or whatever.
How did you get the postdoc?
Oh, the guy who hired me, he did his postdoc at Penn State, and I worked with him while he was there. He was my advisor, so it was basically a personal connection. Which I think that's another good thing to know, is that connections play a huge role in finding a job, even in academia. It's very much about who you know as well as what you know.
Yeah.
So don't underestimate the importance of networking.
That's right. That's right.
Yeah.
So, anything else you'd like to share with us?
Yeah, I don't know. It's been 2 hours. I think I'm pretty burned out.
Well, you shared your social media contacts, and so if we have any questions that pop up later on, feel free to email or tweet David. I'm sure he'll respond to those.
I'm always happen to things on Twitter, and I guess if you use the, I don't know if I put my email address in the presentation. I usually tend to try to go for like the tweeting and on Stack Exchange and things, but yeah.
Find him on Twitter. That's the best way.
Anyway.
All right, let's give our
Twitter is good. Thanks again for this opportunity. It was fun.
All right, thank you very much. We really appreciate it. This was a great seminar.
Yeah, thank
All right.
you.
Thank you. Talk to you later. Bye-bye.
Yep, bye.